Right now, as you're watching this video, you're moving at over 1,000 miles per hour and you have absolutely no idea it's happening. I'm not talking about some cosmic phenomenon or a metaphor. I mean literally right this second you are hurtling through space faster than a fighter jet, and yet you can't feel a single thing. No wind in your face, no sense of movement, nothing. Here's what makes this even crazier. While you're spinning at 1,000 miles per hour on Earth's surface, our entire planet is also orbiting the sun at 67,000 miles per hour. And on top of that, our solar system is racing through the Milky Way galaxy at 514,000 miles per hour. We are moving ridiculously fast on multiple levels simultaneously, and we perceive exactly zero of it. So what's going on? Why can't we feel any of this motion? And more importantly, what would actually happen if we could suddenly feel the Earth spinning? The answer involves some fascinating physics, a few mind-bending thought experiments, and one terrifying scenario that would literally end civilization as we know it. But before we dive into the science, let's start with something that might blow your mind even more. The speed you're moving right now actually depends on where you are on the planet. If you're watching this from Singapore or Quito, Ecuador, which sit right on the equator, you're spinning at roughly 1,037 miles per hour. But if you're in London, you're only moving at about 650 miles per hour. And if you happen to be at the North or South Pole, you're barely rotating at all. You're just slowly spinning in place like you're standing on a lazy Susan. This happens because Earth rotates like a record player. The outer edge moves faster than the center. When you're at the equator, you're on the outer edge, traveling the full circumference of Earth in 24 hours. That's about 24,901 miles in a single day. Do the math and you get over 1,000 miles per hour. But as you move toward the poles, the circles get smaller, so the speed decreases. NASA actually uses this to their advantage when they launch rockets into space. Most launch sites are built as close to the equator as possible because that extra rotational speed gives rockets a free boost. It's like getting a running start before you jump. You're already moving fast, so you need less fuel to reach orbit. The European Space Agency launches from French Guiana. SpaceX uses Cape Canaveral in Florida, and India's space program operates from Sriharikota, all positioned to take maximum advantage of Earth's rotation. It saves millions of dollars per launch. But here's the thing, that speed we're talking about isn't some abstract number. You can compare it to real-world objects to understand just how insane it is. The fastest commercial train in the world, the Shanghai Maglev, tops out at 268 miles per hour. That's impressive, right? Magnetic levitation, cutting-edge technology, the future of transportation. But compared to Earth's equatorial rotational speed of 1,037 miles per hour, that train is moving at less than 1/4 the speed you're spinning right now, while sitting still. Let that sink in for a second. You are currently traveling nearly 4 times faster than the fastest train on Earth, and you don't feel a thing. No G-forces, no wind resistance, no sensation whatsoever. So why is that? What's the secret behind this invisible high-speed journey we're all on? The answer comes down to one critical factor: constant velocity. In physics, there's a principle that goes back to Galileo and Newton. If an object is moving at a constant speed in a straight line, you can't feel that motion from inside the object. The only thing you can feel is acceleration, when speed or direction changes. Think about the last time you were on an airplane, cruising at 35,000 feet. Once the plane reaches its cruising altitude and stops climbing, you can walk around, drink coffee, even balance a coin on your trade table. The plane is moving at 500 miles per hour, but you don't feel it at all. Everything inside the cabin moves with the plane at the same speed. But remember what happened during takeoff when the plane was accelerating down the runway? You felt pushed back into your seat. Or during turbulence, when the plane suddenly drops or jerks, you feel that immediately. Or when the pilot banks into a sharp turn, you feel yourself leaning to one side. That's acceleration, a change in velocity, and your body can detect it instantly through your inner ear and your sense of balance.
Earth's rotation is like that airplane at cruising altitude. It spins at a constant speed, completing one full rotation every 24 hours. There's no acceleration, no change in speed, no jerking or stopping. Our rotation has been remarkably consistent for billions of years. Everything on Earth rotates together at exactly the same speed. The ground beneath your feet, the air you breathe, the buildings around you, the oceans, the mountains, everything is locked into the same rotational motion. There's zero relative motion between you and your environment. Relative motion is the key term here. We only perceive movement when there's a difference in speed between two objects. If you're on a train moving at 60 miles per hour and another train passes you going 80 miles per hour, it looks like that train is only moving 20 miles per hour relative to you. But if both trains are moving at 60 miles per hour side by side, the other train appears to be standing still. Relative motion equals zero. On Earth, there is no relative motion between you and the planet's surface. You're both spinning at exactly the same speed, which creates the illusion of being completely still. It's not that the motion isn't real, it's that your frame of reference is moving with you. This is why when you jump straight up in the air, you land in the exact same spot. If Earth's rotation somehow didn't affect you when you left the ground, the planet would spin beneath you while you were airborne, and you'd land hundreds of feet away from where you started. But that doesn't happen because when you jump, you carry Earth's rotational momentum with you. In physics, we call this conservation of momentum. You and the Earth are part of the same rotating system. When you jump, you don't suddenly escape that system. You remain coupled to it. It's the same reason why if you toss a ball straight up inside a moving car, it doesn't fly backward and smash into the rear window. The ball carries the car's forward momentum with it, even after it leaves your hand. Now here's where it gets interesting. Earth's rotation isn't perfectly uniform. We're not moving in a straight line. We're actually moving in a giant circle, which technically means we're constantly changing direction. And changing direction is a form of acceleration. So shouldn't we feel that? You'd think so, but the circle we're moving in is so incredibly large and we're moving around it so slowly relative to its size that the acceleration is absolutely tiny. At the equator, the centripetal acceleration caused by Earth's rotation is only about 0.03 meters per second squared. That's roughly 0.3% of the gravity pulling you down. In other words, the force trying to fling you off the planet due to rotation is about 300 times weaker than the force holding you on the planet due to gravity. You literally cannot feel it. But don't worry, we're going to talk about what would happen if that balance suddenly changed, and trust me, it's absolutely catastrophic.
All right, let's run a thought experiment. What if Earth suddenly started spinning faster or slower? What if the rotation changed enough that we could actually feel it? Let's start with a sudden stop. Imagine Earth's rotation just slammed on the brakes and came to a complete halt in an instant. You might think, okay, we'd suddenly feel still, like getting off a merry-go-round, but the reality is far more terrifying. Remember, you and everything on Earth's surface are currently moving it up to 1,000 miles per hour. If the ground suddenly stopped, but you didn't, you'd keep moving forward at 1,000 miles per hour due to inertia. It would be like getting ejected from a car traveling at supersonic speeds. Everything not firmly anchored to the planet would be launched eastward at incredible velocity. Buildings would crumble, oceans would slosh across continents in massive tsunamis. The atmosphere itself would keep moving, creating winds stronger than any hurricane that has ever existed. We're talking about an extinction-level event that would make the asteroid that killed the dinosaurs look tame. Nothing on the surface would survive. But let's try a less catastrophic scenario. What if Earth just slowed down gradually over time? Say the rotation decreased by 10%. At first, you might not notice much, but strange things would start happening. Days would get longer. A 24-hour day would stretch to 26 or 27 hours. This would mess with every living thing on the planet.
Our circadian rhythms would be disrupted. Plants and animals that depend on day-night cycles would struggle to adapt. Weather patterns would change dramatically. Earth's rotation drives the Coriolis effect, which influences wind patterns, ocean currents, and storm systems. Slower rotation means weaker Coriolis effect, which means different weather patterns. Regions that are currently temperate might become extreme deserts or frozen wastelands. And here's something really weird. If Earth slowed down, the centrifugal force pushing outward at the equator would decrease. Gravity would effectively get stronger at the equator, and you'd weigh slightly more. Not enough to notice day to day, but measurable on a scale. Now, let's flip it. What if Earth started spinning faster? If rotation increased by just 10%, days would shrink to about 21 or 22 hours. That might sound convenient, more days in a year, right? But the consequences would be severe. That centrifugal force at the equator would increase. The faster we spin, the more force pushes outward, trying to fling things off the planet. At a certain speed, that force would overcome gravity. Scientists have calculated that if Earth spun about 17 times faster than it does now, roughly one rotation every 84 minutes instead of 24 hours, the centrifugal force at the equator would equal gravity. You'd become weightless. Objects would start floating away. The oceans would be flung into space. And if it kept accelerating beyond that, everything on the surface would be ripped apart and scattered into orbit. Earth would literally tear itself apart from the inside out. The planet would flatten into a disk and eventually disintegrate. So yeah, it's a very good thing we can't feel the Earth spinning, because if we could, it would mean something has gone catastrophically wrong. But here's a fun question. If we can't feel Earth's rotation from the surface, could we feel it if we left the surface?
The answer is yes, but only under very specific circumstances. If you could somehow jump high enough, hundreds of miles straight up, and completely decouple yourself from Earth's rotation, you would indeed land in a different spot when you came back down. While you were floating up there, Earth would continue rotating beneath you, and by the time you landed, the ground would have shifted. Of course, no human can jump hundreds of miles high, but we do have something that can: rockets and spacecraft. When astronauts go to the International Space Station, which orbits about 250 miles above Earth, they're moving at roughly 17,500 miles per hour. They have to move that fast to stay in orbit. But here's the thing. They're still moving eastward in the same direction as Earth's rotation. In fact, they launched eastward specifically to take advantage of that rotational speed. From their perspective, looking down, they can see Earth rotating beneath them. They watch the sun rise and set every 90 minutes as they orbit. They see continents and oceans sliding past. It's one of the most dramatic ways to observe Earth's rotation directly. But you don't need to go to space to observe the spin. There are ways to detect it right here on the ground. The most famous demonstration is the Foucault pendulum, invented by French physicist Léon Foucault in 1851. It's a massive pendulum that swings freely in any direction. If you set it swinging in a straight line and watch it for several hours, you'll notice something strange. The direction of the swing appears to rotate slowly. The pendulum isn't changing direction. Earth is rotating beneath it. But from our perspective, standing on the rotating Earth, it looks like the pendulum is drifting. This was one of the first direct experimental proofs that Earth rotates. You can see Foucault pendulums in science museums around the world. There's a famous one in the Pantheon in Paris and another at the Smithsonian in Washington, D.C. Watching one swing over the course of hours is a weirdly mesmerizing way to witness Earth's rotation in real time. There's also the Coriolis effect, which we mentioned earlier. This is the apparent deflection of moving objects caused by Earth's rotation. It's why hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. The rotation of the Earth beneath the storm causes the air
to curve. Pilots and long-range artillery operators have to account for the Coriolis effect when plotting their trajectories. If you fire a missile at a target hundreds of miles away and don't adjust for Earth's rotation, you'll miss by a significant margin. And of course, there's the most obvious sign of Earth's rotation, the sun. The sun doesn't actually rise in the east and set in the west. The sun is staying relatively still. We're the ones rotating. Earth spins eastward, which makes it look like the sun is moving westward across the sky. Ancient civilizations didn't know this. They thought the sun orbited Earth. It wasn't until Copernicus and Galileo that we realized the truth. We're the ones spinning, not the sun.
If you set up a camera on a tripod pointed at the night sky and take a long exposure photo, you'll capture something beautiful. Star trails, streaks of light tracing circles around the North Star. Those trails aren't the stars moving, they're Earth rotating beneath them. It's a stunning visual reminder that we're living on a spinning ball, hurtling through space. So, bringing this all together, why can't we feel the Earth spinning? Because Earth rotates at a perfectly constant speed, and we rotate right along with it. There's no relative motion, no acceleration, no change in velocity to detect. Our bodies can only sense changes in motion, not motion itself. It's the same reason you don't feel like you're moving when you're on a smooth flight or cruising down a highway at steady speed. Motion without acceleration is invisible to us. But make no mistake, the motion is real. You are spinning at over 1,000 miles per hour right now. You're also orbiting the sun at 67,000 miles per hour and racing through the galaxy at over 500,000 miles per hour. We live on a cosmic roller coaster moving at incomprehensible speeds through the universe, and yet we perceive none of it because everything around us is moving with us. It's a beautiful reminder of just how weird and wonderful physics can be. The universe is full of motion, chaos, and energy, but from our tiny perspective, standing on the surface of a rotating planet, everything feels perfectly calm and still. So the next time you're sitting quietly, remember you're not sitting still at all. You're on the ride of your life, spinning through space at breakneck speed, and the only reason you can't feel it is because the universe has designed the perfect illusion of stillness. Pretty wild when you think about it. Thanks for watching. If you enjoyed this video, make sure to hit that subscribe button and turn on notifications. We've got more mind-blowing science content coming your way. And if you want to support the channel, check out the links in the description below. Now, if you'll excuse me, I'm going to go sit down and try not to think about the fact that I'm currently traveling faster than a speeding bullet.